Most of you have finished maybe the first third of the homework. And so if we go to about right here, we're essentially just looking at combinations of forces, right? And they've essentially given you angles, they've given you magnitudes of forces, and angles of forces. These angles are both the same, in fact. And you're going to resolve these forces into components, add them together, and then recombine them into a single vector. How do we do that? Fairly simple. It's just time consuming is all. Okay. Forces me to start the meeting. So here's your diagram you're drawing they gave you in the homework. Your free body diagram, you'd make your coordinate system, x and y. Then that looks like an x2. X and y. And normally we'll just put our object of interest, in this case the skater, at the origin, and then we'll draw our forces. And we have two forces in this case. We have the force coming from the bottom left up towards the top right, and one coming from the top left down to the bottom right. And when we draw forces like this, we start from our object of interest and go outward. So we have one force this way and one force this way. And the two angles that they give us in the picture are the angle between this axis here, which they're actually calling the z-axis, now that I realize this. And this is quite important when you're doing your homework, is notice which way their axes are pointing. Their axes are pointing x positive to the right and z positive down, or towards the bottom of the page. So we need to fix our axes. And then from that positive z-axis, they have the angle theta 2 and the angle theta 1 from the negative x-axis. So make sure we get our axes correct. We have to make sure we get our axes correct, we have to fix this. This is actually z. Go back here and get rid of this. So that's our positive z, that's our positive x, and we have these two forces that are pointing in these directions. Now, remember that they gave us the angle for this one with respect to this axis. So it's a good idea to extend these axes out this way. You could just extend it like this, I suppose. And remember where that vector was. So if we extended this vector down here, they gave us this angle. If I extend this vector here, they gave us this angle, I believe. Nope, they gave us with the negative x-axis. So it's actually this angle that they gave us. These two angles are theta and theta, so we got to do just a little bit of geometry. That means that this angle up here is theta, right? And this angle over here would be 90 minus theta, if you wanted to use it. You don't have to use it, just to label all the angles. And then this angle here is theta, so that means this angle here is theta. Now, this can confuse people to have their axes upside down. If you want to flip this over and redraw it, that's fine. You can do that. No big deal. Up to you. It doesn't really matter where the axes are as long as you remember where the vectors are pointing. Which way the vectors are pointing is what's really important, right? So you know that this vector is pointing this way. I don't remember what they name these. This is force 1. So this is force 1. And this is force 2. All we really need to do is remember which way they're pointing, and we'll be good to go. So let's look at each of these forces individually. If we look at force 2, and I really think this is valuable to look at these individually in this problem, because the coordinate axis is so weird. We have our x here and our z here, right? So that means that our x component for this is going to be pointing off in this direction. So this would be, and this is force 2, so this would be force 2x And our z component is going to be pointing this way. So this is F2z. Right? And the angle right here is the theta. So how do we do this? We can either, you can see that this vector here would be the one that goes up here to complete this triangle, or this one would go over here to complete this triangle. It doesn't matter either way. But since we have the angle theta up here, I go ahead and move this vector up here to complete the triangle. That means my F2x, and let me just get rid of that, my F2z I'll put over here so that you can see that that's actually F2z. And this is F2x up here now. My F2x is actually opposite the angle theta. So F2x is going to be equal to F2 sine theta. Because it's opposite the angle. F2z is next to the angle theta. So F2z is going to be F2 cosine theta. Right, and that's my trigonometry part. And that's fine. These two things now I'm going to circle, try to circle them anyway, because those are going to help me later in the problem. And I do the same thing for the other vector. The other vector is pointing down this way. This is my x direction. This is not my z direction. My z direction is down here. Just do that so I can remember what sign I'm going to be using. And F1 is here. And that means that I have an F1 in the x direction look like this, F1x. And I have an F1 in the z direction that's going to look like this, going down, F1z. And the angle that I have in this triangle is theta right here, from there. And so the F1z is now going to be opposite my angle. So that's going to be F1 sine theta, because sine is always the opposite. F1 sine theta. And my F1x is going to be the F1 cosine theta. Now I'm going to go ahead and look at all these things and assign them some signs because I know which directions they're pointing. This is just going to be helpful for me. This F2z is pointing up, which is the opposite direction of the positive direction in z, which is down. So this one is going to have a negative sign in front of it in the end. I just need to make sure that it ends up that way. This one is pointing in the positive x direction, which is to the right, so this one's going to have a positive sign associated with it. This one is also pointing in the positive direction, so it's going to have a positive sign associated with it. And this one is pointing down, which is in the same direction as the z, which is the positive direction for z. And you could even write in your unit vectors if you wanted to do that, because this one right here is, since it's pointing in the negative z direction, that's going to be negative k hat direction, right? So this is actually pointing in the negative k hat direction. This is in the positive x direction, so that's the negative, or so that's the positive I hat direction. This one is also positive I hat direction. And this one's the positive k hat direction because it's pointing down. So you actually know what unit vectors are going with each of these if you wanted to do that. And why do I do it for this one? Because this is such a weird coordinate system. This is a weird coordinate system pointing off to the right and down. It's x and z instead of x and y. When they do funny things like that, sometimes it's just useful to set it up so that it makes it nice and clear what you're doing in the end. And what are you doing in the end? You're going to add your z components together to get an overall z component. You'll add your x components together to get an overall x component. And then, and because we know F2 and theta and F1 and theta, we're going to get numbers. We're going to get, when we add our F1x and our F2x together, we're going to get some number here, whatever it is. Right? We're going to get some number, and then that, and because the F1 and the F2 in the x direction are both positive, then this number definitely has to be positive, so we just make sure that it's positive, make sure we haven't made any mistakes. And that's going to be multiplied by the I hat, if we want to put it in vector form. I can't remember if they, yeah, they actually do have it. You have to actually answer this in vector form here for that total force. And then the acceleration in vector form. Well, what would the acceleration be? Well, they actually do tell us the mass of the skater. So once we figured out this one would be our F total in the x direction. vector, adding these two vectors together. And we do the same thing with y, the f1y, the f2y, right? And we get a vector component for the y, or sorry, the z direction, not the y direction. I keep forgetting it's the z direction. And remember that this one here is going to be positive and this one will be negative when we add them together, so that you could possibly get a negative or a positive answer, not sure until you do the math. But you're going to get some f total in z now from the second time, from the second one, you do this. And those two vectors that are pointing in the x and z direction are going to make your total vector. So you just write them together as this one times I hat and this one times k hat. Write that in, put it in for your first answer. And then the second answer, the acceleration, is equal to that force total vector that you just wrote down with its two components. And you divide it by the mass of the skater, which they give you. So each term in that force is going to be divided by this, in my case, 65 kilograms. In your case, it might be a different number. And then the third one says, what is her acceleration assuming she's already moving in the direction of the force F total? So that's a bit of a trick question. The total force is going to be off in this direction somewhere. She's being pushed this way and this way, so it's going to be off in this direction somewhere-ish. Off to the right, and maybe up, maybe down a little bit, most likely up a little bit. So if she's being pushed off to the right and up a little bit, and she accelerates with some certain amount of acceleration from rest, is that any different if she's already moving in that direction? Does it change your acceleration if you're already moving at a constant velocity? Anybody have any ideas on that? Does a constant velocity change your acceleration? Yeah. The acceleration then will just change that velocity. Instead of changing you from zero, it'll change you from some initial velocity, right? So it doesn't really change anything. So this one is really much simpler. That one's a little involved just because you have to write all the vectors out. But this one's quite a bit simpler. How do we do this problem? The force forward is related to this force, this pushing force. The actual force and the, there are two forces acting on it. There's one pushing at an angle and one pushing it straight forward, or pulling it straight forward, you can think of it as. How do we add these two forces together in the direction that the block is going to accelerate? First of all, which way is this block going to move if this is on the ground like this? Which way is this block going to accelerate? It's going to accelerate to the right. So that makes perfect sense. But what part of this force is going to actually contribute to that acceleration? The force here that's coming down at an angle, it's not all going to contribute to accelerating the block, because part of it is going to push it down into the ground. And that force down into the ground is going to be counteracted by a normal force and cancel out. So you only need the x portion of this force, or the horizontal portion of it. So you just take this force that's on the left, multiply it by the cosine of 30 degrees, and then add it to the force on the right. And then you're done. Does that make sense? Number 9, you have the weight of an astronaut. Remember that weight is a force. So you can apply Newton's law to it, where you know the acceleration is some particular acceleration due to the planet on that planet. In this case, you're on the moon. Their weight is only 308 newtons, right? You know the acceleration on the moon is 1.67 meters per second squared. So this weight, which is the force, is equal to the astronaut's mass times this acceleration. So 308 equals mass times 1.6 meters per second squared. That means you divide the 308 newtons by 1.6 to get their mass. That seems like a, well, that's, okay, they have their spacesuit on in their backpack too. I'm like, that's one heavy astronaut. They've got a serious mass. Humongous. Okay. Didn't know they let astronauts go to space if they were that big. But the suit makes a difference. So anyway, that will calculate, so if you want to know what they weigh on Earth, how much they weigh on Earth, you calculate their mass, and then you multiply it by 9.8 instead of 1.6 to get the force they feel on Earth. And then the mass, of course, you already calculated. And then what is the mass on the Earth? That's a trick question, isn't it? If you know the mass of the astronaut on the moon, do you know the mass of the astronaut on the Earth? Does the mass of an object change? No. Not unless you're going close to the speed of light. And even then, it doesn't actually change. It just increases in momentum. Here we have a fireman with mass m. Here's the fire alarm size on the pole with some acceleration. And it's less than g in magnitude. Why is the fireman's acceleration less than g when he comes down the pole? Gravity, the gravity constant, little g, tells us how fast we accelerate towards the Earth without anything resisting us. So he's grabbing the pole, right? So there's some force upward as he grabs onto the pole. So there's some friction on the pole, and that actually changes the acceleration, lowers his acceleration, which is good. Because, you know, the average firehouse has 20-foot something ceilings. And if you fell 20 feet, you'd hurt yourself bad, if not kill yourself. So you can calculate the force that he has to apply to the pole to counteract this acceleration by setting up Newton's second law. Some of the forces, you have the force of gravity, which is going to be m times g, minus the force of the pole on the pole, which you don't know what it is yet, but it's going to be mass times something. And that has to equal the mass times acceleration that they actually encounter, they actually experience. So you can write that equation. And in that part, they really just want the equation. Then they give you some numbers to plug into the equation, and you get a force. Now, on these problems where it just says ebook in my thing here, do they give you the option to try another version still? They do? Unless it's multiple choice, right? But okay, I was just wondering that because my version of this doesn't show that part, so I wanted to make sure they were still allowing you to do that.
I think your version also has different numbers from ours.
Oh, it definitely does. Everybody's, yeah. Yours is different than hers. That's one of the features of these online homework assignments today. This is also why I don't really care if you guys just sit down and tell each other how to do the problems. I think that's actually a very good way to learn physics, is to have somebody sit down and say, this is what I did, you try it. So, here we have two ice skaters playing tug of war. They hold on to opposite ends of the rope, and one person accelerates, Hank accelerates 1.10 times greater than Harry. And they want to know what is the ratio of Hank's mass to Harry's mass. Now this is actually, some people, I haven't switched, I guess it doesn't matter. Anyway, some people really struggle with these, so I want to show you how to do them. It's actually simpler than most people think. Here they've told us something very important. They've said the magnitude is 1.10 times greater than the magnitude, right? So magnitude of Hank, magnitude of Harry. And if when they say that it's 1.1 times greater, that means you take the first one that is greater than or less than, depending on what they say here. But anyway, you just take the first one and divide it by the second one. It's that simple. So the first one is Hank. Yeah. So Hank's acceleration. So you take acceleration of Hank and you divide it by acceleration of Harry. And that's how you start this kind of a problem. And then you put an equal sign and you say, what is acceleration equal to? Right? Well, acceleration is equal to force over mass if you look at Newton's second law and solve it for acceleration. So it's the force of Hank, I'm going to call Hank K, and the mass of Hank over the force of Harry, which I'm going to call R, over the mass of Harry, R. Okay? So now we've got a compound fraction here. But the interesting thing is that there's something that is the same in each of these. What is it? When you're pulling on somebody, what are they doing back to you? Pulling on you. And what do we know about those two pulls? They are equal and opposite. So the force that Hank feels is equal to the force that Harry feels. And the force that Hank pulls with is equal to the force that Harry pulls with. So these two things actually cancel each other out. So we end up with 1 over, don't forget that there's still a 1 here, 1 over mass of Hank over 1 over mass of Harry. Now this can be simplified. How does this get simplified? Yeah, we multiply reciprocals and cancel everything out. And what we end up with is we flip this fraction and get rid of the compound fraction, right? So we end up with mr over mk. So that means that the acceleration of Hank over the acceleration of Harry is equal to the mass of Harry over the mass of Hank. And that's actually what they're asking for. Well, they're asking for the mass of Hank over the mass of Harry. The mass of Hank over the mass of Harry. So they're asking for the exact opposite of what we just solved for. Right? What we have here. So we just take this thing and flip it over. We take acceleration of Harry over acceleration of Hank, and that's our answer. So acceleration of Harry over acceleration of Hank is the answer. Now, the previous problem actually is going to help you to solve the next problem. Instead of a pull, it's a push, but it's the same concept, right? The forces that they feel when they push each other are the same, and their masses are different. So their accelerations are going to be different, but they're going to be inverted the difference is going to be inverted, right? So you can use the equation in the previous one, replace the names, and put in the correct masses and solve for the ratio of equations. And then you can use that ratio to solve part C. And to answer part A and B as well. So fairly straightforward, number 12, if you got number 11 right. Now we just talked about this one, Colleen and I. Remember we talked about as tension, if you apply a tension to a rope, even if the rope is, going through a pulley system, that tension extends through the rope. So there's that same tension everywhere. In this particular case, this pulley right here is connected to this foot. Right? Usually there's a strap there. They should have put a strap in there to show that it's connected to the foot, but they didn't. But so this pulley is pulling on this foot, but there's two tensions pulling on this pulley because there's a rope on either side. Right? And it's the component that is horizontal of each of those tensions that's actually pulling. The upward part of this tension and the downward part of this tension cancel each other out and don't really pull on the foot at all. But the 2x components here, so if you take this tension times the cosine of theta and multiply it by 2, because it's the same angle and the same tension on both sides, then you'll get the amount of tension pulling on this foot. So what happens, if you want to make this tension increase, what do you need to do? What do you need to change here? Well, you go through and you say, well, the length of the rope, does that change anything? Does changing the length of the rope change the tension in the rope? Or does it change the force here? No. There are two things. If the length of the rope doesn't change it, then it's either the angle or the tension. And they already said the tension's not going to change. So it has to be the angle. So it has to be either this one or this one. So what change, if we make the angle smaller or bigger, is going to make this bigger? If we pull more up and more down, that's not going to affect anything, so we cancel each other out. But if we pull more sideways, so if we lower this angle or decrease this angle, then it's going to pull more on that foot pedal. And this is just like the one we looked at in the book in class. Didn't we do a tightrope walker problem? I think we did. Trying to remember if we did one. It would be in here. They're right there. So in this example, they're doing the same exact problem as that homework problem. This is in the other forces section, a couple sections back. But here are the forces that you're dealing with. You have the tension in the rope to the left side, tension in the rope to the right side, and the leftward component and the rightward component actually cancel each other out in this case, whereas the upward component of each of these forces is the thing that actually holds the tightrope walker up. These long right and left components make the rope really, really tight, but they don't actually hold the climb rope. So if they're asking you for how much tension is in the rope, then you need to calculate this, which is the tension times the cosine of the angle. And then you need to add it to this one to get that tension. If you want to know the amount of force holding up the person, then you calculate this one. If they give you the weight of the tightrope walker, if they tell you how much the weight is of the tightrope walker and the angle, then you can calculate the tension from that by saying that 2 times this is equal to the weight of the weight of the tightrope walker. So then you say 2 times tension in the y direction, which is 2 times the tension of the rope times the sine of the angle, equals m times g, the weight of the climber. Then you can solve for the tension in the rope that way as well. So they have all those equations here. They have, here's your net tension in the x direction. That's the left and right tension right there. You have your net tension in the y direction, right, which they solve here, and then they solve these equations using some ratios to solve for the actual tension of the rope. Then here is the equation. This is one of those very useful equations where the tension can be used to relate to the weight. So tension and weight are both in this equation right here. So that's a useful one. And this, of course, is the same problem, but backwards. Instead of a rope being used to hold up a tightrope walker, we're going to have a chain connected to a car and a tree, and we're going to push on the rope to pull on the car. Right? So instead of the tightrope walker, we're moving a car. So we push this way, and the force that we push with this way is counteracted by the vertical component of this tension force. And the horizontal component of this tension force pulls the car out, as long as the other horizontal component doesn't pull the tree out. As long as this tree right here is really, really strong on the ground, you can pull a car out really easily this way. Then the box on the inclined plane. So so the box on the inclined plane is a exercise in rotating axes for most people. You can do this without rotating your axis if you want to. That's completely up to you. In this particular case, it won't change much because there's no friction. So that's fine, but when there is friction, which there will be in the next chapter, you'll definitely want to rotate your axes. But in this case, you have the force upward. Let's get to our whiteboard here. So here's your inclined plane, here's your box. Force upward this way. And we also know that there's weight on the box, which is downward. That's the weight of the box, which is m times g. And there's no friction, so these are the only two forces. So the reason that I say it doesn't really matter if you rotate your axes is because if you rotate your axes, you're only going to rotate into one of the directions of these two forces. Since there are only two forces, you're still going to have the same amount of work either way, so it doesn't really matter. So let's just leave our coordinate system as is. We'll just leave our x direction horizontal and our y direction this way vertical, and that's fine. That means we're going to resolve this force into two components, x and y. It's going to have force in the x direction and a force in the y direction to complete this triangle. And this actually makes it quite simple. You can see that this angle here, theta, is going to be the same as this angle, so that's theta. And that means the force in the x direction. Oh, I did forget something. I forgot one force. Which force did I forget? The normal force pushing up on the box, right? I forgot the normal force. So there are two forces pointing in this horizontal, or to this parallel and perpendicular direction. So it's probably good to rotate our axes after all. Let's do that really quick. Let's see. Erase already. So we'll rotate our axes. Instead of x, y like we have here, we'll have x prime and y prime. And this is why they do the x prime, y prime thing. I think they do that in the book, right? They do this to show that it's different than the regular x, y, so it's x prime, y prime. So we've rotated our axes to line up with the slope here. And that means our force is now pointing in the x prime direction, F. And our normal force is actually pointing in the y direction, the y prime direction, normal force. And it's only our weight that is pointing in some other direction, straight down. So only our weight needs to be resolved into components. This weight has a component in the y direction that looks like this, and a component in the x direction. So the weight has this component and this component. So this is weight x prime, no y prime, and this is weight x prime. So, and this angle here will be our theta now. So the weight vector has two components, x prime and y prime. The x prime is opposite the theta, so that's going to be equal to the weight times the sine of theta. And then the weight in the y prime direction equals weight cosine theta. But we have more forces involved, and we need to add them all together to make our total amount of force. But what is it asking for again? So we go through all this thing, we draw all this, and we can't remember what it's asking for. So it says what force must be applied to cause an acceleration of 8.8 meters per second up the plane. So they want to know how much this force is if we get an acceleration up the plane. So what we need to do is we need to look at our x prime and y prime and see which one of these we care about. Well, in the x prime direction, that's up and down the plane, so that's the one we actually care about. This one we would care about if there's no friction, if there was friction, but since there's no friction, it doesn't matter, because this one would affect the friction because of how hard the box is pushed against the plane. So this one we don't care about because there's no friction. But in the x prime direction, we need to write down all of our forces. We need x prime, w, the weight in the x prime direction, which is w sine theta. What other forces do we have in the x direction? Just the force F. So we have the force F in the x direction. So those two forces add together have to equal our acceleration, which they've told us what it is already. Force plus W, and remember that the W, the x prime one here is actually the opposite direction of F. So this one is actually a negative W sine theta because it's pointing in the negative x prime direction. So let's erase some things here. So the force total in the x prime direction, force total in the x prime direction, is equal to the force pointing in the positive x direction, so it's positive. And then the weight force, which is pointing in the negative x prime direction, so that's negative weight sine theta. And those are all of our forces. They have to add up to equal the mass of the box times the acceleration of the box, which they've already told us. They've told us that the box is going to accelerate up the plane 8.8 meters per second. So our acceleration is 8.8 right here. Our mass is the mass of the box. So in this equation, we know the weight of the box, we know the angle, we know the mass of the box, and we know the acceleration of the box. You plug all these in and solve for F. We're done. Or we solve for F and plug them all in. And then we have a spring one, a spring problem. So the spring problems are actually quite simple. In the book, they tell us the spring equation. It's K times X, where K is the force constant of the spring. So you just plug in the numbers and solve for K. In this one, it's a free body diagram of a ball hanging from a string. Which one of these is going to represent that? Weight down, tension up, right? A car moving in a horizontal road, which one's going to represent that? This one? Yeah. The force pushing it and the friction opposing it, opposite directions. See you later. Oh, did you see my email about train? Oh wait, never mind. You're not doing this. Never mind. I keep thinking you're doing this. You're not. Never mind. Okay, so yeah, this one right here, right? How about this guy?
I'm not entirely sure yet. I know that it's not the last one. I think it's either the first or third one because both of those have the capital F in the right direction.
The weight, which way does the weight always point?
Does it always
It always points down, so it has to be one of these three. Right? Which way does the normal force push?
sort of
Normal force, which way does the normal force push? It always pushes normal to the surface. What does normal mean? Perpendicular. So it's always perpendicular, right?
Let's say one that features the normal force. Maybe I misunderstand this.
Let's see here. I suppose that they're actually counting this force pushing up as including the normal force, I guess. So this one, this force up is actually the force of the ground on the thing, on the jogger. And that's fine. So this is actually, this includes the normal force in it already, I
So
suppose.
which one's correct? Because the dot you have filled in is the second one. So it's,
So it would be this one. And traffic light.
last one. Because the T1 and T2 are in the right place and it's the right angles. The way it's going down.
So you're saying that T2 is going to have a higher tension than T1? Because these ones, so T2 is on the right and T1 is on the left, you're saying, right? Okay.
Yeah, because in the diagram there, T1 is on the left and T2 is on the right. And 41 degrees is on the left and 63 degrees is on the right.
Yep. That's correct. Good. All right. Any other questions?
Not now.
Okay.